Hi everyone, and welcome to today's Tech in 10 session. My name is Niels, and I'm excited to share some thoughts on retrieval augmented generation at scale, especially how we can leverage Amazon Redshift in the process. Let's dive in. When it comes to retrieval augmented generation, or RAG, the first thing many of us consider is a dedicated vector database like FACE or advanced search algorithms such as HNSW. But what if you're already running a stable data warehouse like Amazon Redshift, which doesn't have native vector search functionality? Adding a specialized vector store typically means creating yet another system to maintain, raising costs and complexity. Fortunately, a novel approach shared by Rajiv G shows that you can implement vector search right within Amazon Redshift. This way, you can avoid spinning up new infrastructure and manage all of your data in one place. Check out the link on the slide for more details. One of the key steps in RAG is converting your text data into vectors, often called embeddings. With Amazon Bedrock, you can generate these embeddings at scale. The process might look like this. First, you unload your target data from Redshift. Next, you run a batch embedding job on Bedrock. Finally, you upload these embeddings into Redshift. This keeps the entire workflow streamlined, letting you leverage Redshift as your single source of truth for both your primary data and your newly generated embedding vectors. Handling large-scale embedding jobs may take time, so asynchronous processing is key. By using the Redshift Data API, you can kick off an embedding job through Bedrock and periodically pull for the job status. This approach keeps your system responsive while the embedding tasks run in the background. Once complete, you'll get the results and can move on to the next steps, like storing or analyzing those embeddings in Redshift. Now let's talk about how to query those embedding vectors in Redshift. The brute force method is straightforward, but not always efficient. For each query, generate an embedding, then calculate the distance between this query vector and every stored vector in your dataset. After all comparisons, you rank by similarity or distance. While conceptually simple, brute force searching doesn't scale well. Imagine doing 1,000,000 comparisons for 1,000,000 records. Let's explore how we can optimize this. Unlike a brute force approach, where you compare every vector in real time, k-means enables you to do much of the heavy lifting beforehand. Because k-means is an unsupervised learning algorithm, it doesn't need labeled data to figure out how to group your vectors. It just clusters them based on similarity. When a query arrives, you generate its embedding, find the closest cluster centroid, and then compare the query vector only to that cluster's members. This significantly reduces the number of comparisons you have to make. For example, 1,000 clusters might cut 1,000,000 comparisons down to just a couple thousand. When it comes to running RAG on Redshift, there are definite benefits, especially if Redshift is already part of your data stack. You can avoid spinning up new systems, simplifying both cost and management. You can also leverage SQL-based RAG workflows if that's your current approach. However, since Redshift lacks native vector indexing, you'll rely on workarounds like k-means, which can introduce limitations. If your clusters overlap significantly, or you set the number of clusters too high, performance could drop. It's a balance between convenience and raw speed, so think carefully about your specific use case. We've seen how k-means can help by clustering embeddings and reducing brute force comparisons. Another important concept is k-nearest neighbor, knn, search, which looks for the k most similar vectors to a given query vector. Knn can be done in different ways. A brute force knn method compares the query vector to every vector in your dataset, which can be time-consuming. Alternatively, you can optimize knn with approximate methods, like HNSW or IVF, to speed things up at the cost of slight approximation. Ultimately, the choice depends on the scale of your data and your performance needs. If you need to handle very large datasets, approximate approaches to knn, known as ANN, can be a game changer. By relaxing exact matching a bit, you dramatically speed up search. Two popular techniques are HNSW and IVF. HNSW is known for being extremely fast, but uses a lot of memory, while IVF is more memory-friendly, but maybe slightly slower. For massive, real-time needs, These specialized solutions typically outperform a brute force or basic k-means approach. Whenever we talk about optimizing queries, be they vector-based or otherwise, it's important to remember that not all databases are created equal. Broadly, we categorize them as OLAP or OLTP systems, each with different design goals. OLAP focuses on complex queries and analytics over large datasets, while OLTP is optimized for high-volume transactional work. Understanding these distinctions helps you pick the right tools and approaches for your RG use case. Here's a quick comparison between OLAP and OLTP systems. OLAP is typically about long-running queries to gain insights from large, combined datasets like dashboards and trend analysis. This often means it's okay if queries take minutes or even hours. On the other hand, OLTP systems prioritize immediate transactional consistency. Think e-commerce checkout or banking transactions, where performance is measured in milliseconds. For RAG workflows, an OLAP-style database like Redshift might be more appropriate for analytical queries, but if you have to embed real-time transactional data, you might need a different approach. As we wrap up, it's important to strike a balance between getting the performance you need and keeping your architecture simple. If you already use Redshift, building RG features on top of it can be highly convenient, especially for moderate-sized datasets. That said, if your use case demands lightning-fast search across billions of records, specialized vector databases or advanced KNN algorithms might be worth the complexity. Ultimately, the best choice depends on your data size, performance requirements, and operational constraints. That brings us to the end of our session on ArgG using Amazon Redshift. I hope this session gave you insights into ways you can work with embeddings and k-means clustering without immediately needing a whole new vector database. Of course, specialized solutions exist for more demanding workloads, but if you're already using Redshift, this method can be a solid starting point. Thank you for joining me, and I look forward to hearing your questions and experiences in applying these ideas.